Okay. It's a great pleasure to have Karl Jansen, which is director of the Center of Quantum Technologies and Application at DESY, as a speaker of this colloquium. The colloquium will focus on the application of quantum computing to lattice gauge theories. We know that in quantum chromodynamics, Lagrangian contains gluons and quarks, but actually we see hadrons. So this is this phenomenon of confinement, and in an attempt to understand this mysterious quantum phenomenon, Wilson proposed in the 70s to analyze gauge theories by using the Feynman idea of making calculation in quantum field theory through an integral of all possible virtual space-time configuration of the fields which are involved, but instead of using our continuum space-time, discretizing space-time into a finite lattice to make such integral finite. And this allowed to use classical stochastical methods to treat the first simple model, like QED, for example, in 2+1 dimensions, and then gradually, as the power of the computer increased with supercomputer, also QCD was tackled. However, some phenomena, such as the particle collision and hadronization, for example, are still intractable even with such supercomputer. Nevertheless, Feynman in the 80s suggested that a quantum computer using entanglement might be more efficient than a classical one to simulate quantum systems. And the current technology, in fact, allows us to start making Feynman's dream come true and to apply it in particular to lattice gauge theory. Jansen is a world-renowned leader in both classical and quantum simulation of lattice gauge theories. He received his PhD in Aachen and his habilitation in Hamburg. He then was at CERN. In 2000, became the leader of the research group in particle physics at the John von Neumann Institute of Computing. And in 2022, head of the Center for Quantum Technology at DESY. Among his awards, I would like to mention the Wilson, so you see Wilson Lattice Award in 2011, and the ERE Chair Award for Quantum Computing for Excellence in Science and Technology in 2022. So thanks to his career, he's the ideal guide to enter in this new rapidly developing field of physics covered by this colloquium, where fundamental interaction and quantum technology meet. So please.
Higher?
Yeah, sorry.
No,
I'm so sorry.
It's all fine.
That's it.
So what I said is thank you for this very kind introduction. I really feel now motivated to give the colloquium, and you also gave already a motivation why I'm doing this, and I'm really thankful for this. So what I want to do is I want to give you an introduction, then I will discuss quantum electrodynamics to make it really not too high-dimensional. We will stay in 1+1 dimension. I indeed will show you something in real-time scattering experiments. And I also go classical and show you what we can do to organize your flights in an airport if you have connecting flights more efficiently than what you experience at the airport today. It's of course not true, but that was the goal. And then I want to introduce the Center for Quantum Technology and Applications and then conclude. So we have something that is called the archive, where we scientists, we submit our preprints such that everybody in the world can see what we have done. And if you go to this archive, you see that quantum computing is applied to quantum biotechnology, of course to quantum chemistry. This makes a lot of sense, But you also find paper where they use this already for medicine. They construct quantum batteries, and even loan collection optimization for the stock market is done on this quantum computing. And I was thinking, okay, so portfolio optimization, yes. But then I saw a paper where they had quantum natural language processing approach to musical intelligence. So I was thinking, now they're also using quantum computing for music. And I was shaking my head and was, no, that goes too far. Then I met my students in the afternoon with a coffee, and I told them about the paper here, and I told this is going too far. And then one of my students raised the hand and said, I'm also doing this. And since I really estimated this student, I said, tell me what you are doing. And then about half a year later, we had ourselves a paper about quantum computing for music, sonifying the DESY model. This is how it can go. And it's really a very interesting field. We have now 3 papers. We are giving concerts. So it's really fascinating. But let's come back to something else. This is a quantum computer. It looks very nice. You can put it in your living room. You can stare at it. And that's it. To be a bit more serious, this is also a quantum computer from the inside now. And the quantum chip, the quantum chip here is down here. And you have all these mechanisms here to cool down the chip. You have a shielding. The chip is shielded to 50,000 times less than Earth's magnetic field, which is really dramatic. It is in a high vacuum. The pressure is 10 billion times lower than atmospheric pressure. And it's cooled down to almost 200 times colder than interstellar space, to 0.015 Kelvin. I'm coming from DESY. We are constructing superconducting magnets. So our engineers know what cooling is. But when I show them these numbers, they are so impressed. And they can say, and they say, we have no idea how to do this. And this is all to avoid that the quantum chip down here gets into any contact with the environment. Because as soon as it comes into contact with the environment, the wave function collapses, and you cannot use the quantum chip anymore for any calculation. And you see really here a very aggressive roadmap from IBM. They started with promising machines with 400 qubits in 2022, more than 1,000 qubits in 2023, and more than 4,000 qubits in 2024. And even they promised to have machines with 10K or 100,000 qubits, with some of them being error-corrected. Now, this was the roadmap in 2021, and as it sometimes happens, if you have such a roadmap, you are not really fulfilling it. So we are at the moment with quantum chips that have about 200 qubits. But it's developing. And this claim of having error-corrected quantum chips is not only IBM alone, but also Google promises about 1 million qubits in 2030 with at least 1,000 qubits error-corrected. So this is where we are going. Towards the end of the century, we will have error-corrected quantum computers. And this will really change the way we are doing computing. You can then use these machines as you use your laptop now, but with quantum algorithms. And you can really start this now. It's not magic. What the companies provide is a Python programming language. And they provide also a lot of libraries that you can use to really write a quantum program. And you only have to change a single line to go from something that you write on your laptop and test on your laptop to bring it to the machine. And then you can really do a quantum computation. This is what I said. They provide simulators that run on your local laptop so you can test the programs. And then you can use the hardware through a cloud service, which was built on a reservation system. This is constantly changing, but you can use it. And there are also a lot of documentation. There are tutorials and examples. For example, you can look in this IBM textbook that you find here, which means that after this colloquium, if you're interested, you can start actually directly now, write your first quantum program, generate a belt state, and run it on the hardware. It will take you 1 to 2 afternoons. Yeah, please stay and don't start now, okay? Okay, so what do I want to do? I want to do something that is really a benchmark model for us to see what we can do with a quantum computer in lattice gate theory. And this is the Schwinger model with this two-dimensional quantum electrodynamics. We quantize this with the Feynman path integral, where you integrate over all degrees of freedom the gauge field and the matter fields, which are fermions. You have an action principle, so you have the action for the fermions, where you have an antifermion here and the fermion there. You have a gauge covariant derivative and you have a mass. The gauge covariant derivative is written in the standard way, as you know it from electrodynamics. This is a classical action, and the gauge action is just the integral over the field strength tensor that you have here, and which you also learn in electrodynamics. What we do then, we put this on a lattice, and to show how we do this in principle, so we introduce a lattice, so you have lattice points here. The matter fields live on this lattice point, so a psi lives here, and you, instead of continuous time and space, you make space and time integers, and then you discretize the action, so instead of an integral, you have a sum. Then you have, at the moment we don't have gauge fields, you have the derivative, this d mu, and this d mu is simply 1/2 of the Napler operator star and the Napler operator, and this is nothing else but the difference of fermion fields at the point x that is shifted by the lattice spacing. The lattice spacing goes from here to here, and the fermion field at the lattice point x. And psi star is just with a negative sign. And you can see, if you expand this here, then the lattice spacing drops out and you really get back the continuous derivative. So this is how we do the discretization in a very naive way. The not so naive point here and ingredient of the action is the second derivative term here, and I will not go into details, but if you do this naive discretization, if you wouldn't have this term here, then you would have unwanted modes in the system that would not reflect the physical system that you want to simulate. But with this term, you can remove the so-called doublers. And as a side remark, unfortunately, when you do this, it breaks then chiral symmetry. For the gauge fields, there was really the fundamental observation by Wilson that it is not the gauge potential that you know from your electrodynamics lectures that is the fundamental object, but it is the parallel transporter. It is this U that we call the link operator, and this is related to the gauge potential through this exponentiation. And basically, with this U, you can now define a gauge covariant derivative. Before we had just the fermion fields at neighboring lattice points, and now you multiply this with the parallel transporter, which does nothing else but transports a charge from this lattice point to that lattice point here. And this is then leading to a local gauge invariance, which is very important in high energy physics. You can multiply this psi of x with a function g of x, and you can multiply this parallel transporter with a function g of x at the point x, and a g star at the point x plus mu. And then if you build the action with these objects, you find the local gauge invariance on the action, on the lattice, which is a very, very important principle. This leads to the action then, so I explained to you, we use this link operator, which lives on the link here. For the gauge part itself, you have something like a plaquette, so you have this link operator that goes from here to here, then from here to here, and back here. And since you have a closed loop, under these gauge transformations that I showed you before, this action then becomes gauge invariant. And you can show that when you send the lattice spacing to 0, so you are going back to the continuum, then you find back the field strength tensor that you want from the continuum. And then, in the end, you have really the full action. So you have the real part of this plaquette operator. It's multiplied by a parameter beta, which is 1 over the coupling square. And you also have a mass term, and here this gauge covariant derivative with the second order derivative term, which gets rid of the unwanted modes. And then you can compute physical observables. So you integrate over all possible field configurations. You have e to the minus s, and then you put an observable there, for example, the proton mass or anything else that you are interested in. You do this lattice discretization that I told you on the previous slides. Then you do a translation into zeros and ones, and then you put this on a very powerful computer. I'm very curious now. In every talk that I give, I ask the question, who knows what computer this is? Ariana, you are not allowed to answer. No one. This is the Leibniz computer. It was built already in the 17th century. You see this wheel here, so you can use the wheel, and you could do multiplications with that machine, and it really worked. It's built, it's in one museum, I have forgotten where, but it's really a machine that could do additions and multiplications already then. Okay, I told you about the Schwinger model. I want to give you a flavor. If you really, what you said, if you really want to do lattice QCD, if so, we would go from, let's take a square lattice of 40 times 40 points in the Schwinger model, which is 2D, and let's go to QCD. QCD lives in 4 dimensions, 3 space, 1 time dimension, which means if you take this example of a 40 by 40 lattice, the computational cost is a factor of 1,600. The gauge fields in the Schwinger model come from the group U1. If you go to QCD, you have to use SU3, which gives you a factor of 8. The Pauli matrices that you use in the Schwinger model goes to Gell-Mann matrices, which gives you another factor of 4, and the spinors in the Schwinger model become 12-component complex vectors, complex spinors, which gives you a factor of 24, which means that you have a total factor of more than 1,000,000 for a computation in lattice QCD compared to the Schwinger model. So if you would have a simulation in the Schwinger model that takes you 1 hour, it takes you more than 10 years in lattice QCD. And that's really the difficulty and the challenge that we were facing in lattice QCD. For the experts, we also need a non-perturbative minimalization there, which is really conceptually extremely important for QCD. And there's really a large activity of theoretical calculations of the standard model with particle interactions. And if you're interested, there is this review, there is the so-called Fleck group, and they really give results that are obtained in lattice QCD. And we brought it to a point that we now can really simulate in fully physical conditions. So we have the physical value of the up quark, the physical value of the down quark, of the strange quark, and the charm quark. And this then becomes really very, very important. And we not only simulate QCD, we also simulate the Higgs-Yukawa sector of the standard model. We are simulating supersymmetric models. And this is all based on Markov chain Monte Carlo methods. So this is very nice. But I wanted to give you one example. I don't want to go really into detail, but there was really a big puzzle. There was a theoretical prediction that, or we seem to understand that actually the quarks itself are not enough to produce a spin of the proton that is 1/2. And it was a big puzzle because it was found experimentally that actually the spin of the quarks are too less. They cannot explain that the proton is a spin 1/2 particle. And with lattice QCD, what you can do, you can look at the individual contributions. Well, sorry for that, this was, okay. You can really look at the individual contributions of the quarks, the up, down, the strange, and measure what is the contribution of these quarks to the spin of the proton. And you can also determine the contribution of the gluon. And only if you include the contribution from the gluon, you find that really the proton can assume this value of a spin of 1/2. This is one example. It took us, I think, 10 years to produce this plot in fully physical conditions, taking all the quarks into account, but now lattice QCD can really explain this. So lattice QCD is fantastic. It's super. It's really totally great, and I worked on this for many, many, many years. But I realized there are also dangerous animals on the lattice. And these dangerous animals come for very important questions. For example, if you want to understand the phase diagram of the universe, then what you have the temperature, and you also have the density of particles in the universe. And what lattice QCD can do, they can do simulations along this axis here, basically at very small or vanishing particle density, but lattice QCD with Markov chain Monte Carlo methods cannot explore the complete phase diagram. So all this here is not available for us by doing lattice QCD calculations. And that's, of course, the biggest part. And from lattice QCD, we can, using Markov chain Monte Carlo methods, we cannot say whether what is the inner structure of neutron stars? Are there new phases that are predicted? What is the phase transition to the quark-gluon plasma? And all these things. Also, what happens in heavy ion experiments like at CERN. So this is really not available for Markov chain Monte Carlo methods. And the reason is that we have not a probability density when we add these terms here. So we do not understand really the origin of today's universe. Also, if you're interested in topological terms, which are CP violating, and where we believe this could contribute to the matter-antimatter asymmetry in the universe, we cannot do this with Markov chain Monte Carlo simulations. If you're interested in real-time evolutions of systems, Euclidean lattice QCD is not possible. But there is a solution, which is very nice. And the solution is you can use the Hamiltonian formulation. Now, Hamiltonian formulation has a problem by itself because it grows exponentially. You have a basis state here, and you have a coefficient function, and this coefficient matrix has 2 to the n entries. So it scales exponentially. And if you remember this game with the rice corn that was promised to somebody, if you start with putting a rice corn here, 2 there, 4 there, 8 there, and so on, at some point, even Berlin, this is the television tower in Berlin, will be covered under rice, which means that practically, if you use naively this Hamiltonian formulation, you will run out of steam very soon. However, there is a solution. Actually, there are 2 solutions. The first solutions are tensor networks that are really followed here in Padua very strongly with the group of Simone Montangero. They work extremely well if you have a gapped local Hamiltonian. Then they show a very fast, maybe even exponential convergence. They become, however, costly when you have a lot of entanglement in the system. So if you go towards a phase transition, or if you want to do really long real-time evolution. However, it's a really powerful method to study things, to study quantum field theories. The alternative is quantum computing. That's a really conceptually clean path. We are not there. I told you we have quantum computers with 200 qubits. That's certainly not enough to simulate quantum chromodynamics. And at the moment, these machines are really noisy. So the results that you get if you don't do anything are really noisy, and you cannot get any reasonable results out. Nevertheless, here my focus on the colloquium is really on quantum computing. And I'm coming back to the Schwinger model, because the Schwinger model is interesting really from the physics point of view. It has bound states, so it shows the phenomenon of confinement, like in QCD. It is asymptotically free, the coupling goes to 0. So if you have charges and you measure the coupling and you bring the charges close to each other, the coupling goes to 0. It is exactly solvable for 0 fermion mass, which is excellent, because then you have an analytical benchmark against your simulations. It is super renormalizable. and you can add topological terms. So something you cannot do with Markov chain Monte Carlo methods. And therefore, it is a valuable test laboratory for QCD itself, but also you can test your algorithms for situations where Markov chain Monte Carlo fails. And this is the phase diagram that we want to get out of it. So this is the continuum Schwinger model Hamiltonian. So you have now operators, you have fermion operators, you have the gauge potential operators, which will be transferred again into these link operators. You have the mass term, you have the electric field operator, and here you have something that serves as a topological term. It's a background electric field, but it is, in a sense, a topological term. And if you study this, then you find, if you plot the mass divided by the coupling G as a function of this theta parameter here, then you find that if the mass over G is large enough, you find the first order phase transition, or better to say, you speculate, you should find the first order phase transition. If this mass parameter is too low, then there is no phase transition anymore, and you have a smooth transition. And this first order line is supposed to end in a critical point in the second order phase transition. Oops, that's not me. I see my stuff still. Okay, thank you. Yeah, ends in a critical second order point. And this phase diagram really is very hard, if not impossible, to explore with Monte Carlo methods. So let's use quantum computation. If I want to use quantum computation, I have to formulate the Hamiltonian on a lattice. And this goes very similar as I told you for the action formulation. So we have again, the fermionic fields. We have this parallel transporter, this link operator. We have the nearest neighbor interaction. We have a mass term, and we have the electric field operator and the background electric field. So this L0 is simply theta over 2 pi. Okay, now comes a little mathematics. It's not extremely complicated, but you can relabel your field operators in a certain way, and then you can express everything in Pauli matrices through the so-called Jordan-Wigner operator, and then you get a form of the Hamiltonian, which is not so important to read here, but it's important to realize these are all Pauli operators. So these are operators that act on a two-component state. So if you can formulate your problem in such a form, you can use it directly for a quantum computation. It's ready to use. Okay. You can also do the same for the operators, for the observables that you want to study. It's like for the electric field density or the particle number. You see this is just phi, and through Jordan-Wigner transformations, you can again express this in terms of Pauli matrices here, the third Pauli matrix, or here the first Pauli matrix, such that you can really measure the qubit information that you get out from the quantum computer. This I skip. And how you do this? You do this through a variational hybrid ansatz algorithm. You have your qubit Hamiltonian, I just showed it to you, and then you generate a quantum circuit. What is a quantum circuit? This is an example of a quantum circuit. So you have the qubits here, they are initialized to 0. Then you have rotation gates that act on the qubits and bring this in superposition or in different states. You also have entanglement states, and you see that these gates, they have parameters, and I will come back to this in the previous slide. And this is a quantum circuit that we use and that we run from this initial state here. We set these parameters to certain values, and in the end, we measure the state that we obtain here. For the experts, we have developed a so-called dimensional expressivity analysis of such circuits, which allows us to really identify which of all these gate operations are not necessary, and you keep the expressivity. That's for Simone, Pietri, and so on. So we have this Hamiltonian, the qubit Hamiltonian. We have these parameters. We initialize these parameters in a certain way, for example, random. Then we run this parameterized quantum circuit with all these parameters. We measure then the state, and the state that we have measured, we compute the energy, which means we compute the expectation value of the Hamiltonian that we want to have. So now we have the energy value, and we have the parameters of the quantum circuit, and then we give this value to a classical optimizer, and he looks at these parameters, at the energy landscapes, and says, no, 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 this is not good. I think the minimum of this, the minimal energy, which is really the target of all this, you should use another set of parameters. Then we give these parameters back to this here, to this parameterized quantum circuit, now with the new parameters from the classical optimizer. We run through this again, we measure it, we measure the energy, give the parameters and the energy to the classical optimizers, and then you execute this loop here until you really find the minimum energy. And you not only find the minimum energy, you also find the corresponding eigenstate, the wave function. Okay, this I showed you. And this is another example. These are actually the circuits that we have used for the computation I will show you. So these are rather complicated structures. You have SO4 gates, also SU4 gates. You can decompose it in these rotation gates and entanglement gates. The details are not so important here, but this is how it looks like. And this is what you actually program for your quantum computer by using this Python programming language. And you have also different structures of the circuit. So here you have a brick structure, so you really build a wall, or you have a ladder structure, so you go like this way. And it's really, you have to try these things. There's nothing that tells you, if you have this model, use this circuit here as the elementary operation and use this structure here, and you will find a solution. No, you have to test this. You really have to sit down. You have to try all the circuits, all the structures before you find a solution for the Hamiltonian you are looking at. And the solution for other Hamiltonian might look again different. This is really an art, and my students and postdocs, they are really spending a lot of time and of finding optimal ways of encoding this into a quantum computer. I think I can maybe. So what I told you is these quantum computers are noisy. And what often happens is you do a quantum computation, let's say for a small system, where you can do exact diagonalization. So you know the result, you should get out this, let's say for the energy, and what you get out of the quantum computer is a value here. Now you say, what can I do? And you might think about ways of correct this to bring this down, and funnily enough, the way to do this, or one way to do this, is to add more noise. So you can insert into your observable basically a unit operator. So you have UU dagger, which is the unit operator. And with any addition of a gate, this corresponds to a gate, you add more noise in the quantum computer. So then you have this unmitigated value, and you have values that are amplified in the noise. And what you can then do, you can do a linear extrapolation to the noiseless case, and you find the mitigated value, which hopefully is then closer to the value that you want to obtain. Now, this sometimes works. In this case, we really could extrapolate very nicely to the exact value, but there are also cases when it doesn't work, and you cannot really find the optimal extrapolation to zero noise. So you have to be very careful also with this method, but anyhow, it really helps us to come closer to the result that we want. And this is now the result that we want. So I showed you this phase diagram here, and here we did a simulation basically down here, and we wanted to see whether we see any sign of the phase transition, and we shouldn't see any. And we did tensor network methods, we did exact diagonalization, and we also did hardware runs. And what for me is very nice is that you don't see anything, namely meaning that all these points here collapse, and you see that with the hardware run on the quantum computer, you get the exact results. This is a lot of work. You have to do error mitigation like this zero noise extrapolation, but if you work hard enough and you have somebody from IBM who sits next to the machine and calibrates it every hour, then you can get such nice results. And if you now go to a large mass in this regime here, you should see really this first order phase transition. And indeed, if you look at the electric field density or the particle number, then at a certain point you really see a jump both in the electric field density and the particle number. And we went up to a system of size 6, meaning using 12 qubits, and you really see these jumps as indications of a first order phase transition. And again, in the plot, you have results from exact diagonalization, but also hardware runs. And again, they fall on top of each other, which demonstrate if you work hard enough and you know what the quantum computer is doing, you can get already for this low-dimensional system very good results. We didn't stop. I will not explain this, don't worry. We didn't stop in 1 + 1 dimensions, but we went to 2 + 1 dimensions. The Hamiltonian becomes much more complicated, and I will not go into this, but I want to mention that we have invested the running coupling with matching to Markov chain Monte Carlo method. We have looked at the electric flux configuration for a Coulomb confinement and string breaking regime of the static potential, and we have also developed a lattice Chern-Simons Hamiltonian in 2 + 1 dimensions, and I cannot resist, but for the experts in the room, this is the Hamiltonian, just to prove to you that we have really developed this, and this can really serve as a microscopic description of topological materials. And we really hope to find applications for this that we can really use on the quantum computer to really investigate materials. Maybe at that point, does anybody has an urgent question or you want me to finish? I see Marco, he likes this Hamiltonian, yes. No, then I continue and we go to something else. We go to particle scattering, and we were really motivated and intrigued by a work that was done here with tensor networks, which was really very nice. This was really a scattering experiment. A scattering experiment using tensor networks. So you have 2 wave packets that start here, and then you let them collide, and you see what happens after the collision. And this is for different parameters. And you see when you change the parameter of the model, and then you sometimes see that then entanglement is created after the collision. This is indicated by this shaded area here. And if you change the parameters even more, then you see that you can really generate a lot of entanglement after the particle collision. I found this really the first very nice illustration that in a particle collider at LHC at CERN, there is entanglement generation after the collision. And it depends a lot on what you are doing, at what energies you are probing this, what are the masses of your particles, and so on. And you can see this here clearly. So, thanks, Simona. We wanted to do this on a quantum computer. We were not looking at the Schwinger model, but we were looking at the so-called threading model. This is, again, you have the kinetic part of the fermion, the mass part, and then you have a 4-fermion interaction. You again have the lattice version of it. Basically, you couple the fermions on neighboring sites. And you can go to a spin representation through the Jordan-Wigner transformation. And then you get this object here, which looks complicated, but it's straightforward. And the only thing that is important here, again, that you express this in terms of Pauli matrices, such that this is immediately ready for a quantum computation. Okay? And then we looked at how can we generate a Gaussian wave packet. For the experts, we used Givens rotations. With this, you can really generate Gaussian wave packets on the quantum computer. And we did the same as the group here. So we generated these Gaussian wave packets here and here. This is now free fermions, and what you see, what happens if you don't have interaction. then basically these wave packets go through each other. This is periodic boundary condition, so this wave packet goes here and reappears here, and so on. But nothing interesting happens here. The interesting part starts, and then we put it on the quantum computer. Let me just check whether, yeah. Let me just check, and here the quantum circuit really becomes very massive. It's really very massive. All these blocks here contains dozens of rotation gates, entanglement gates, and you really put this all together in such a complicated quantum circuit, and you really hope that you can do something with this, and you hope that the machine is not too noisy, that your results are too messy. But we did this, and you can see this here. So this is now the interacting case. Here you see again the free case. The wave packets just cross each other. But when you change the coupling, let's make it positive. When you change the coupling close to 1, then you see that you have a repulsive force. So the wave packets scatter here, and then one goes in this way, the other goes in this way. So you really have a repulsive force that you can measure on the quantum computer. And here you see also we plotted the entropy, what happened after the collision. We also plotted the subtracted entropy, which means the entropy of the single wave packets when nothing happens. And you see when the coupling is strong enough, so here, you really still have entanglement. You can really see this. For me, this always looks like an alien that is coming out, but I'm alone with my opinion in the collaboration. And here's now a real hardware run. So this is one run that we did classically, and we took slices of these scattering experiments, like here and here. So this is the position, and this is a particular slice here. And what we compared is really the result of a classical calculation with the result that we got from the quantum computer. And again, you can see that we really got very nice results from the quantum computer, which is very promising to study scattering on the quantum computer. Okay. So let's shift gear. We were in the quantum world. Not everybody of us is in the quantum world, but many of us are in the real world. So we looked at a classical optimization problem, namely a flight gate assignment problem. The flight gate assignment problem is that you have incoming and outgoing flights, and you want to reach your outgoing flight, so you want to have the shortest connections between connecting flights, which is not the intention of the airport. The airport wants you to take the longest flight, the longest connection, because you have to visit the duty-free shop, buy your cigarettes, your wine, your perfume. Okay, so we optimize this, once for you and once for the airport. For me, this is really an interesting problem. It is a classical optimization problem, and the question here is really, will I be able to reach a quantum advantage? This is really the question that we have. And what I found really intriguing here is that we got real data from an airport. So there was an airport in Germany that said, okay, if you want to test this, we can give you real data of the flights, how it goes in the airport. So what I will show you, these are not fake data or let's say artificial data on which we are working, but we are working on the data from this airport. I'm not allowed to say which airport it is, but it is real data. And what you do here, you define a binary variable, which is 1 if a flight I is from the whole set of flights is assigned to a gate alpha from the set of all gates. And it is 0 otherwise. This set of zeros and ones, f times g, you transform into a binary variable, -1 and 1. So this is an eigenstate of the third Pauli matrix sigma z. And then you construct a Hamiltonian that is of this form. It has a diagonal part. And then it has all possible connections. So you combine all sigmas, j's, and k's. These indices runs over this set here, f times g. And in this matrix, qjk, you encode all the times that you need for going to your flight that you want to connect to. And the task is to find the lowest energy of this system here, which would correspond to the shortest path. And for this, we use, again, this variational eigensolver that I showed you before. So this is a hybrid classical quantum algorithm to find this lowest path. And what was also interesting for me, if we would find an algorithm that finds or that gives us good solutions of this, then the same mathematical descriptions can be used for other problems like in traffic, logistics, particle tracking, and many other classical optimization problems. So let's see where we are. We started with something that is called the QUBO formulation. So this ratio here is basically the success rate. Do we really find the shortest path? And you see, we started with this first implementation, very low. This ratio should be 1. And you also see, this is a log scale, that the success rate fall down exponentially fast. So we were really very, very disappointed, and we said, no, quantum computing is not useful for such problems. Then I got, after half a year of filling out forms and going to the embassy, a Chinese postdoc. And she had really very good ideas. Without going into details, we used the binary encoding. We used the reformulation of the Hamiltonian through projectors and using conditional value at risk methods. That's for the people who are knowledgeable. And what we found with these improvements is that this success rate stays essentially constant as a function of the number of lifetime gates, which correspond to the number of qubits. And this was a very nice result, and it basically scales even. I think now we went to 24 qubits, and other members of the group are extending this even to 64 qubits, which means that at some point this really becomes realistic. And after these very nice results, which shows that you can use quantum computers for doing classical optimization problems, we were contacted by a company in the US, IonQ, who are constructing quantum computers based on trapped ions. And they asked us, can we do this with our system on a real device? And we said, yes, of course, we can try this. So we went to a situation with 8 qubits, where we really did VQE runs and we converged. We also did this for a larger system, for 12 qubits. And the really interesting outcome here was that if you do an exact ideal simulation, these are these blue points here, you converge after about 100 iterations of this hybrid algorithm. If you add quantum mechanical noise, which we call shot noise, you also converge, but you converge earlier, like here. And if you do the quantum run, you converge even earlier. And our interpretation was, with this classical optimization, you often run into local minima, and you are stuck there. And maybe the noise on the quantum computer can help you to really get out of this local minima, and you converge faster. That's a hypothesis. It needs to be proven if it is true, but it's a possible explanation. Okay, let me tell you about our Center for Quantum Technology and Application. I consider it as a house. We are an IBM Quantum Innovation Center. We have networking, we have scientific exchange. We have access to the complete quantum computer hardware fleet. We are working together with the government, with industry and academia, and we can give support and access to the quantum computer hardware. They might have to pay for this. This gives us then possible income, but they can also come to us and tell us and ask us how can we do quantum computation, and we train them. And for me, this is really a house. So a house needs flowers and a cat, right, to make it nice. This is how it all started in 2011 with Ariana and Schenk. Ariana is here. And this is where we are now, to build up a group in not so many years. Here, 3 female members are missing. And if you would count with these 3 female members in addition, this group consists of 50% male and 50% female researchers in theoretical physics. raise the hand of the theorist who has a similar participation ratio. No hand, okay. No, I'm really very proud of this, I have to say. What we are doing, I told you the problems in theory. We're doing this classical optimization, classification. This is also for particle track reconstruction, jet classification at the LHC. I showed you the flight gate assignment problem. We are also in the IBM pillar of healthcare and life science, where we explore quantum algorithms for gene and exon classification. We are also doing quantum art. If you are interested, we are doing quantum computer music, and we are doing quantum painting. We can discuss later what this means. I want to point to a workshop that we will be organizing in July, the 9th to the 11th at DESY, close to Berlin. These are weekend projects where really motivated people come together and say, we want to develop this, so this is outside our working hours, but it's really interesting and fun. We are doing factoring, so prime number factorization, which is also done in the group here, Feynman diagrams, matrix models, and other things. I also have an ERA chair, you mentioned this. An ERA chair is a European project that should bring new activities into widening countries. And I got 2.5 million euros to build up a quantum computing group in Cyprus with similar goals as in the center. So we want to develop applications and use cases for industry, government, and academia. We wrote that we want to act as a hub for the Eastern Mediterranean region. This is a bit difficult at the moment, so this is on hold, as you can imagine. And it is, of course, closely connected to the Center for Quantum Technology and Applications. And I usually say, to get this ERA chair, I'm forced to spend like 40% of my time in Cyprus. So I was there in January of this year, in February, I went swimming already in the sea, and it's a hard job. Yes. If you're interested, we made an effort to really write a white paper in high energy physics where this group of people identified what are the applications in high energy physics, both on the experimental and the theoretical side, that can be run now on a quantum computer. And we really gave the examples on what people should be working on. And this we did both on the experimental side and the theory side. So on the experimental side, we identified jet reconstruction, rare signal extraction, beyond the standard model events, parton showers, and simulation for experiments. And we identified the algorithms to be used. The same for the theory side. Again, the problems like real-time phenomena, lattice gate theories, D theories, neutrino oscillations. And again, we identified the algorithms that you can use for the problems that you can run already now. We did the same for healthcare. So this is what is the potential for quantum computers to enhance biomarker discovery. So biomarkers are things that puts you whether something on the gene is okay or is not okay. So these are markers, and we want to identify them. And you can see that we really identified a number of algorithms and problems where we believe that quantum computing can be useful. So let me summarize. You mentioned it already, Feynman had this vision that you should use quantum computers to study quantum systems. But it took more than 40 years to start really realizing this vision. And we are just, since a few years, in the position to have real quantum computers that you can use from your laptop. And now you can do this. And we are doing this in experiment. We are looking at particle tracking. We are investigating Boltzmann machines or quantum neural networks. In theory, we are studying these low-dimensional billion, but also non-abelian models in 1+1 and 2+1 dimensions. We are looking at real-time phenomena like scattering. I think soon we come into the area of demonstrations. These are proof of principles, what I have shown you. But now we are coming in the area of demonstrations, which means for me that you have machines with more than 100 qubits and a circuit that I showed you with more than 100 gates. So very, very deep. And this will help us to identify and evaluate applications for quantum computers. So this will really tell us, if you have these machines, what should you put on the quantum computer? Because not all the problems are suitable for a quantum computer. But with these demonstrations, we can identify this you should put on a quantum computer, develop this further, this leave out. Besides the development of the quantum computers, we really need further developments in the algorithms and methods. We cannot stop with what we have. All the algorithms that we are using here are basically copied from the classical side, and then we made it quantum. We need more quantum algorithms like Shor's or Grover's that are really tailored for a quantum computer. And if we can really use such large system sizes and this depth, this can really allow us to evaluate the scaling of the problem with the number of qubits, which would allow us to see where is the break-even point, where quantum computers become advantageous compared to classical methods. And we can look at the scaling and predict where this will happen. And then we can find out where is the quantum advantage, for what and when. And in the future, of course, we will have this fault-tolerant quantum computing, which will really change the game and really make this a practical thing that everybody can use, and you don't have to understand how to error mitigate and all the things. Yeah, and this is the quantum computer music book. We have a chapter, and if you're interested, you can order this and read what we are doing in quantum computer music. Thanks a lot.
Thank you very much for this very interesting talk. There are questions. So I start with two, one more physical and the other more crazy.
Mathematical question.
So, no. One was, what about the process of hadronization? Do you have some...
People, I mean, again, in the Schwinger model, there are some quantum computing experiments that look at hadronization, yes. It's in an early stage as the one that I showed you here, but people are looking into this. They're also looking at how to compute parton distribution functions, really what is the quark content of the proton. This is all being looked at the moment in models like the Schwinger model. So we are starting to develop the ideas, the algorithms, and maybe in some years we can do this for QCD.
The other is more crazy. I don't understand what you mean by a quantum art, I must say. What is the idea which is behind this quantum in the art?
Quantum in the art. This is, you know the development in painting. You have these classical paintings. And then people said, I want to do something new. And then you got Picasso. You got even things like Richter. This is 192 colors. And what we are doing with Ariana and others is we want to use quantum computers to transform classical paintings. The prime example is Picasso again, maybe. He used classical masterpieces and he transformed it in his style. So what we are doing, we are taking classical masterpieces like Narciso from Caravaggio, and we transform it with a quantum computer to get a new piece of art. And then we have a digital model of it at Ariana. She's really painting it back as a human on a canvas. And something similar we do with quantum computer music.
Okay, so questions?
First of all, thank you very much for this nice and also stimulating talk. No, I want, at some point, you mentioned neutrino oscillations, just a curiosity. I was wondering what you plan to compute, I mean, using quantum computing for the neutrino oscillation phenomenon?
Essentially the oscillation frequency, yeah. So we have some input with some masses, and we have some model for the oscillations, which we can transform basically again into a generalized Ising model. And then we can play with the parameters of this model, and we can see how the oscillations are varying with these parameters. And then we can translate this back really to the masses of the neutrinos. Okay? And this is, of course, again, this is a benchmark model, so this is not really predicting the mass of the neutrino. But this is something that gives you at least a hint what could be the masses for the neutrinos such that you see the oscillation that you observe.
Does this provide different results from what we do analytically in computing neutrino oscillations? I mean, because
well, it's a time evolution that you're doing, and time evolutions are always very difficult to perform, right?
Yes,
you have differential equations, but here you have really a way, like with tensor networks, to really follow this time evolution, like we do with the scattering experiment. It's the same idea.
Thank you.
So you've briefly mentioned that you have some activity also on gene search. So can you elaborate on that? Because I don't know what you're doing. So
what we are doing, you have a gene, and the gene is very complicated. You have different regions in the gene, and the most important regions in the gene are the so-called exons. The exons are the active regions in the gene. So on the exons, the protein couples, and the protein goes away and starts all the mechanism in the body. Okay? And the gene is really complicated. So there are some markers in the gene that, that tells, here now comes a so-called exon, the active region of the gene, here it stops, and so on. And you can identify that, that some of these exons are not the exon that you want. For example, you can see that the wrong protein is produced. And this then, of course, leads to illness, right? And what we try to do, we want to really get data for these exons and train a network to identify when is something wrong with this exon and when not. And it's unclear what would be the best quantum machine learning approach for this, but that's the idea. Give us a probe from real patients, and we see, is this exon okay or not? Can we identify this? And this will be done through machine learning processes.
Questions? So maybe I ask another curiosity. Okay. So in the classical case, you said that if you have a theta term, so a topological term, you have problems in dealing with stochastic methods because of complex structure? Or?
Yes, exactly, because the integrand becomes complex, and therefore if you think of Monte Carlo, in Monte Carlo you have an if question. If the action in the process is lowered, then you accept a configuration. Yeah. If you have a complex integrand...
It is not a and here instead you avoid this problem because it's an Hamiltonian...
Because it is an Hamiltonian. And to really say this, when we did the first experiments in this was with the group of Ignatius Irac in Munich, I was always thinking this sign problem, it's called the sign problem, this will come back in disguise. In the end, we will find also with tensor network that there is a big problem that we cannot overcome, but it didn't happen. It simply worked.
So I think I don't see other questions. So we thank again the speaker and